Hello everyone and welcome to session number 8 of this set of videos created to explore programming applications in reinforced concrete. In this session, I will present two Python standalone applications developed with graphical user interfaces to handle two types of analyses. The first one is for flexural analysis of singly reinforced concrete rectangular sections, and the second one is for doubly reinforced concrete rectangular beams. Instead of reading the input data from an input file and then printing the results to an output file like we did in session 7, here the user launches an interactive graphical user interface where the user can insert the required input parameters directly to the interface and then run the application to see the output parameters on the same GUI. It is more of an applet where everything is handled directly on the same screen. I produced the graphical user interfaces that I will present to you in this session using tkinter, which is a standard built-in Python library for creating graphical user interfaces. It is an object-oriented wrapper around the free and open-source TKGUI toolkit, providing a simple and efficient way to build desktop applications that run on Windows, Mac OS, and Linux. Let's look at the first graphical user interface, which is developed for the flexural analysis of singly reinforced rectangular beam cross-sections. Once you double-click on the icon for the applet, a graphical user interface will appear on screen where the user will insert the required input parameters on the left side in the left column, and in the middle and on the right the output parameters will be displayed once the applet is executed. You can see here that the requirements are the width of the beam, depth of the beam, yield stress for steel, compressive strength for concrete, bars in the layer farthest from the neutral axis and bars in the layer on top of it, concrete cover, and diameter of stirrup. Once the execution button is clicked, the results are generated. Now this is a smart template. Let's say that the user inserted information that is not very efficient. Let's say we insert here 20 and then here 22. If we click the execution button, the graphical user interface will switch the diameter of bars to have a more efficient use of steel. Let's say here that we've added 1 bar and 4 bars, and we clicked on the execution button. The applet will switch them to have a more efficient use of steel and will switch number 1, which indicated 1 bar, to 2 bars in a layer, which is the minimum. We can see here that we have invoked the minimum width condition, which means that the available width, which is 250 millimeters, is not adequate to encompass 4 bars. So let's fix that by changing this here to 300 millimeters and click run. Let's change the diameter of bar here to 12 and 12 and have 2 bars only and click run. We will see here that we have invoked the minimum area of steel condition, which states that the number of bars and diameters used are not sufficient to satisfy the AS minimum condition. We can change the input parameters in order to produce a tension controlled cross section. So here I'm going to use 22 millimeter bars and 4x2 and click run. This section is tension controlled. If we use 25 millimeter bars, then we will go into the transition zone. And if we further increase the diameter and use 4x4 bars, then the section goes into the compression controlled zone. Now let's fix these parameters to have a tension controlled cross section. Click run to show you that every time you click run or the execution button, an output file is generated for those who like to document things like me. Here you have a listing of the input parameters, and here you have all the calculations necessary to check the adequacy of the cross-section and calculate the design strength of it. Now let's go and check the other graphical user interface, the one that is developed for the flexural analysis of doubly reinforced rectangular concrete cross-section. Once the user double clicks on the icon of the applet, a graphical user interface appears on screen. Again, the user inserts the required input parameters on the left side, and the output parameters are displayed in the middle and on the right side. The applet is executed by clicking on this execution button here, and every time we execute the graphical user interface, a report is generated in the folder containing the applet. Let's click here to generate the results. You can see in this particular example that the compression steel did not yield, and thus here we can see the iterations of the iterative procedure. If we change the number of iterations to 10 and click on run, we will see that the number of cycles is changed to 10 here. What distinguishes this graphical user interface from the one before it is that it is a bit more advanced. Here you can plot the analyzed cross-section. Let me bring it from the other screen. This is a plot of the cross-section. It shows the time and date. It shows the cross-sectional and material parameters. It shows the status of the beam, whether it has failed or it has passed all the requirements of the ACI code, and it prints the design strength of the cross-section. Not just that, the graphical user interface also prints the ductility graph of the cross-section. So for the input shown on the left side on the original graphical user interface, we can see that this beam is way into the tension controlled zone. If we go back to the graphical user interface and try to change some of the input parameters, let's say here 20 by 22, and try to run, you will see that the template switches the bars. If we add the bars here as 1, 3, and 1, the template will fix the number of bars so that the run that you are trying to conduct is reasonable. If we increase the number of bars here to 25 and 25 and run the cross-section, then the cross-section will be in the transition zone, where you can see that the ball here moved into the transition zone, indicating that the section is not acceptable according to the requirements of the ACI code. Let's further increase the steel. Let's have 4 by 4 and click on run. We can see here that the minimum width condition is agitated, so we can increase the width here and run again. Again, we are in the transition zone, as you can see here. If we try to increase the steel even further, that's 28 by 28, 4 by 2, then we go to the compression controlled zone. Now, I should mention that generating these figures require an extensive amount of coding because you need to use certain libraries in Python. As you can see on the figure on screen, I am using subscripts, I am using Greek letters. To have these figures look exactly as you want them to look, this will require a certain amount of iterations and trials until the figures are adequate. This concludes our session for today. I want to thank you very much for being with me, and I hope that I will see you again in subsequent sessions. Best wishes.